Hey everyone, Natasha here. Today we are going to be discussing and reviewing polynomial regressions. These are more complex models than your simple linear regression and sit within the multiple regression context. We are going to be modeling a curved trend using a hypothetical study on virtual reality based learning environment. So rather than really trying to fit a straight line through our data here today, we are going to allow for that bend and to that curve to better represent the pattern that is in student time spent within the virtual reality space. All right, I'm going to take you step by step through this using R, so let's get started.
All right, everyone, you should have all gotten the link to the polynomial regression GitHub. It is at nkpisano/polynomial dash regression. Once you land on this page, please go ahead and select the code green button. When you do, a drop-down menu will fall. And then if you could please go to download zip. And this will download all the materials that you will need for today. And then from there, you should go ahead and put that new folder wherever you would like. So I'm just going to drag it onto my desktop for simplicity and for easy access. All right. Once you have done that, why don't we go ahead and start opening up a new RStudio project. So I'm going to go ahead and look for RStudio. I'm going to start a new project. And so I am just going to put this new project where that new folder is at, just for time's sake, and for simplicity purposes. So I'm going to put polynomial regression into the portion of the directory name. And I am going to start in a new open section by selecting that open checkbox on the left-hand side. And then I'm going to go to create project button and hit it or click it. And when I go ahead and do that, RStudio will automatically generate a new project for me. Now, I'm just reminding you again that a new R project, think about it as a new folder, a folder where your working directory is set. That means that anything that you go ahead and generate, any new product or deliverable is going to be in here. You also want to put any type of data set in here as well. So that way you can easily just pull it in or read it into the current project. So from there, you want to go ahead and then select new file. And then let's work with an R Markdown document. And then I'm just going to name or give this a title using that title box. And I'm just going to type out polynomial regression. And then I think last time I showed you all that you could generate HTML. You can also do a Word or a PDF. I'm going to go ahead and do a Word document this time just to show you all. And I'm going to go ahead and hit OK rather. And then a new R Markdown is generated. And so I want to remind you all that you don't need any of the default messaging that R provides for you. But what you should do is rather go to that file, uh, the file option in the larger menu of RStudio, and a drop down menu will fall. Go ahead and save as, because currently that RMD file is not saved, and you know it's not saved because it's still untitled in the project. So I'm just going to go ahead and give this a name. So polynomial regression will be the name of this RMD file. So I really want to distinguish the difference between our project and the file that we have just created. One more time, the project, think about as a folder that everything is just stored in. And your deliverable here is going to be your R Markdown code, which then will help you produce an output, which is going to be a Word document. And you want all these things stored within your R project. Never want anything disentangled. Also, you don't want to continue to build within the same R project over and over and over. This actually causes a hassle and can cause conflicting messages, meaning that if you have multiple files that are named the same thing, R doesn't know which file to go ahead and use or to grab or what or a certain source. So you want to really make sure that you are intention that you set the intention to creating a new project. All right. And so from there, I actually am going to do a couple of moving things. I am going to open up that file that we went ahead, that we downloaded, that zip file. I'm going to open it and I'm going to look for the HTML file because that's what we're going to be using. And I'm going to do a split screen here. Okay. Because this file is going to be our lab. All right. And then another thing that I'm planning to do is I'm just going to do a couple of dragging and dropping around real quick. So I probably should have done this first, but I'm going to, within that main folder that we downloaded, that zip file, I'm going to drag my immersive data into my polynomial regression folder that I've just created, or my working directory, or my project. And so I know that it's in there. I can see my R project is there, and then I can also see my RMD files there. And then to triple check that the correct data set is in that working directory, all I have to do here is I just have to check my files. And so sometimes RStudio is a little bit slow. And so all you have to do is select that last extension within the Files tab, that fourth quadrant or that fourth panel, the last extension. I'm just going to do that. And then you can see that my immersive data is in there. Perfect. All right, so let's get started. Now that we have our markdown ready and we are trying to split screen here. All right. So in today's lab, all right, so let's dive into the section that focuses on polynomial regression. I'm going to give you a quick overview. We're going to download some packages. I'm going to define polynomial regressions, and then I'm going to leave you off with an example. And so the example is going to focus on the relationship between immersive virtual reality-based learning and cognitive load. And what you're going to see using polynomial regression is that this relationship between these two continuous variables is going to be a curvilinear relationship. That being said, polynomial regression does the same thing as a linear regression and multiple regression. We're looking at a relationship between two variables. Now, polynomial regression is technically within the context of multiple regression, and I will show you why it is and when you would go ahead and use this type of technique. Also, I'm going to have some time today to show you some really cool diagnostic tools or plots that you can go ahead and use to identify outliers using Cook's distance and leverage. So let's go ahead and get started by first downloading some packages. For my Mac users, go ahead and you can use your keyboard to do this, Option Command I to generate a new R code chunk for that shortcut. For my Windows users, please use Control Alt I, Control Alt I. And then on that HTML file, go ahead and use that clipboard copy option that I have given you all to copy all of those packages within your first R code chunk. A couple things that I'm going to show you here right now is I'm going to just go ahead and Command V for Command Paste. And then I definitely love to write myself lots of notes within my RMD file. So please go ahead and write yourself a note here. You can do this within the R code chunk by doing Shift and then 3 for that pound symbol. And I'm just going to write out packages. You can also add a header here into the main RMD file outside of the R code chunk. So shift and then pound will give you a header. And so this header is a first level header, and I'm just going to type out packages. Okay. And then you can jump and you into this particular level here by using the outline button, which is located within that second panel, the RMD panel or the script panel, and you can select outline. And then you can always just jump throughout your RMD file using those headers. Okay. All right. Before we get into more code, let's go ahead and let's define polynomial regression. So the whole purpose or the goal of a polynomial regression is to investigate a relationship between a dependent variable, a continuous dependent variable, and I sometimes will refer to this dependent variable as response variable. And we want to then try to explain it by some sort of explanatory variables. Sometimes within the education or psychology context, the explanatory variable is referred to as an independent variable. We're going to be taking this explanatory variable to some exponential power, though, and that's what places polynomial regression within the multiple regression context. And so you want to just be aware that even though we're dealing with one independent variable, you're going to be taking this independent variable into some exponential power. In multiple regression, polynomial regression typically only includes one variable because we're taking it to a power, and we're going to be including all the lower terms or all the lower powers within that one regression equation. So we can pop down below and we can see that the successive powers are all included. So in my quadratic function here on my quadratic regression equation, I have my cognitive load is being explained by time spent. This is the linear relationship. But when I go ahead and I add that next term, that time spent to the second power, this then becomes a quadratic equation, right? Because now I have 1, 2, 3 beta terms that I'm going to go ahead and have within my regression equation. And this is what makes it a quadratic equation, a quadratic function. And in my cubic, right, in my cubic polynomial regression model, then I've added a cube term, meaning that I have taken time spent to a third power. And in addition, I also have time spent to taken to the second power or squared, right? And then I also still have time spent. And one more time, all I'm trying to show you here is that we're going to be including successive power terms, making polynomial regression multiple linear regression rather than just simple linear regression, okay? And all of them are really just extensions of each other. So why would you actually do this? What's the purpose? Well, when modeling a regression and you notice, for instance, that there is some sort of curvilinear relationship between the response variable, in this case, cognitive load, and an explanatory variable, time spent, if that relationship is curved, then this is when you would want to go ahead and use a polynomial regression to really have a relationship that is explained appropriately. What do I mean by this? Well, when we have a linear regression, we're saying that a straight line is explaining the relationship, is exemplifies a linear relationship, a straight line between time spent and cognitive load. And in the context of, for instance, if we go ahead and square time spent, then we're suggesting that that relationship is actually kind of bent. There's a pattern to it. And this is why we go ahead and square that term. So that way the relationship can actually mimic the pattern that is in between time spent and cognitive load. I will give you a visualization of this. And regardless or despite us actually adding these exponential terms, either squared or cube or whatever it may be, that your beta terms are still going to remain linear. We're not squaring our beta terms here. So the hypothesis, it does change. And I think it brings me to a place where I need to stop and I need to be reflective and just think about and remind you of the limitations that are often come with polynomial regressions. They sometimes can be difficult to interpret, right? And so that's just something to think about. Another thing is that because all we're doing is either squaring or cubing rather a term, that uh, that these technically variables are the same variable and that they're almost basically dependent upon each other because they are the same. There should be technically a relationship between these variables because all you're doing is squaring and cubing. So that's just another thing to think about because, one more time, these are limitations and they could affect the outcome or the results that you end up finding. Now, when it comes down to the hypothesis, you will still have a null, you'll still have an alternative, just a little bit different. Yes, we are still evaluating a relationship, but then you're also going to have to include these terms such as linear trend or cubic trend. So for instance, for my null, I'm suggesting that the linear trend or the cube trend is the same as the square trend within that null hypothesis. So there is no difference between the modeling linear trend and a quadra trend when modeling the relationship between time spent and cognitive load. One more time. So the linear trend in time spent in a virtual reality course is no different from the quadratic trend, is another way that we can go ahead and say this. Or we can also suggest that the alternative would be that there is a difference between modeling this relationship between time spent and cognitive load when we use a linear trend versus when we use a quadratic trend. The quadratic, for instance, the quadratic term may be a better model, right, for the relationship between time spent in virtual reality than a linear term. I know it's a little bit complicated, but all you're doing is suggesting that you're evaluating a relationship and that relationship depends on some sort of trend transformation. Okay. And so then there are different types of ways or techniques or procedures that we can go ahead and actually implement these polynomial regressions. And so, what do I mean by this? Well, there are ways that we can add the terms, meaning that you can add a degree one at a time. So, one term at a time. For instance, I have three different types of regression models here. And in each regression model, I'm adding a term, right? I'm squaring and then I'm going, and then in my cubic, I add a cube term. And so you just keep adding one by one by one. And so the caveat to this technique to employing a polynomial regression or to determine the best trend for your relationship between two variables here is that you may end up failing to find the best exponential degree term because it stops a researcher from modeling other exponential terms. The moment that a researcher sees that a particular trend can significantly explain a relationship, researchers will stop typically. But then there's also the backward procedure where you start with the highest degree term and remove one term at a time. That is, for instance, if I notice when I plot my linear relationship that I had some sort of maybe bend in my plot there, I maybe wouldn't just go for squaring that one variable, but maybe taking that one variable to the cube or to the third power. And so I would start maybe modeling a cubic function or a cubic polynomial regression. And then going down one by one, meaning that I would start with a cubic and then I would model a quadratic. And then I would maybe, since I already have my linear, I would stop there. Okay. So, one problem or one caveat, one more time, is that researchers may struggle in determining the best starting point because you're relying on a graph sometimes, or even some folks just start at the highest degree possible, and that is six. You should not go beyond six because then you'll have an ill conditioned polynomial regression. And this has all been already investigated by Saber and Lee. All right. And so another limitation that I have to acknowledge one more time is that forward and backward procedures may actually not lead to modeling the same trend. As you can see, some folks stop earlier than others. And then researchers may find that terms may honestly be difficult or confusing to interpret. And we are going to have to really try to work with this type of technique to get the best trend possible that really emulates the pattern that we are seeing in our graphs. Okay. All right, so let's read in the data. So for my Mac users, let's start with a new R code chunk, and that's going to be Option Command I, Option Command I. We're going to be reading in the data. For my Windows users, that's Control Alt I to generate the R code chunk. And so you can go ahead and use the copy clipboard options that I have in my HTML file, or you can start getting that muscle memory, gaining that muscle memory. And then all you have to do is then go ahead, type out read underscore dot CSV, and R will automatically start generating that code for you. Within that, within those parentheses, rather, in quotes, you want to go ahead and type out the file and its extension. So the file is immersive data, and then the extension is a CSV file. You can go ahead and assign a name to the file here, which will make it an object within your environment. So let me show you how you can do that. Either you can use the equal symbol. I love using the equal symbol there. It's old school and I love it. Or you can go ahead and use the assignment operator for my Mac users. Your assignment operator, you can automatically generate it using the shortcut keys of Option and then dash. For my Windows users, that's going to go ahead and be, I believe it's going to be Alt and then the dash. Alt and then dash. All right, and then I'm going to assign this a name, and that's going to be immersive data. You can honestly name it whatever you like. You can name it data since you're only going to be using this file here. And then I'm going to go ahead and read it in by either you can go ahead and click play, or at the end of line 27, command return. You can even do it in the middle of the function itself if you would like to, or the command itself, and it would still run. All right, so our data is read in. How do you know it's read in? It's because within that first quadrant, the environment quadrant or the environment panel, you can see now that immersive data is in there. I have 50 observations with 3 variables. You can even go ahead and take a peek at it by clicking that cute little clipboard symbol that looks like a data frame or data. And you can see that my first column is ID, second column is time spent, and then you have cognitive load. Okay, so one more time spent is going to be my explanatory variable. My response variable is going to be cognitive load. And then from there, I'm simply going to run a linear regression. This is technically the first step that you should have already done, but I just want to show you a couple things and why we are going to employ the polynomial regression. So in order to run a linear model here, I am going to type out just a quick little note, running a linear model between my explanatory, and my outcome. One more time, leave yourself lots and lots of notes because you want someone else to be able to come into your RMD file and know exactly what you've already done for reproducibility purposes. And you should be in the habit of doing this, or get in the habit of doing this rather. And then go ahead and type out LM for linear model. This is the generic R command or function. And then from that linear model, you're going to go ahead and put two parentheses, one opening, one closing. And in between those parentheses there, you want to go ahead and type out your first variable, your response variable, your dependent variable, cognitive underscore load. And then you want to go ahead and do shift tilde. That's usually the symbol that is right underneath your escape key. And then you want that to be explained by time under data or time rather spent, excuse me. So cognitive load is being explained by time spent. And where R can find these, or where R can find the data rather, is going to be comma, and then data is going to equal the immersive data set that you have already uploaded and called in. And then you can go ahead and assign this new linear model to a name or to an object that is going to be stored within your R environment here. And so you can actually use the equal symbol if you'd like to. Just for funsies, I'm going to do it. So model, and then I'm going to just put model LM for the sake of labeling this model as a linear model. And then you can go ahead and hit the play function, or you can go ahead and hit command return. And I'm just going to go ahead and do that. All right. And then from there, you're going to want to print out maybe some of the information related to this model. And so you can look at the coefficients by simply just printing model LM. So copying, pasting, or typing out model LM and then hitting command return will give you those coefficients. Okay. And I'm just typing out a note that I'm only getting coefficients here. But if you really want all of the information related to model LM, to the linear model, you would have to go ahead and use the summary function, which is a base R function. And then you can go ahead and type out the model name that we have assigned our linear model here. And so you can see sometimes I highlight the function itself or the command itself, and then go ahead and do command return, or I think it's for my uh, for my Windows users, I believe it's the same. Okay, and then you will get that information related to um, to the linear model. Now I'm going to keep going, okay? Because the next step that you should be doing is that you should be running an assumptions check. And so when I start running my assumptions checks, this is what's going to be an indication of me having to employ or use a polynomial regression. Okay, so let's start off with first trying to address the linear assumption. So option command I to generate a, R code chunk. And I'm just going to write myself a note. I'm going to put a header here that I'm running assumptions, or that I'm doing assumptions check. Okay. You have to put a space in between the hashtag or the pound and then your title, your header. And so I am going to be using the pipe function. Now, I want to remind you the pipe function is simply just a shortcut, a way that we can reference our data set here. And so you want to go ahead, and for my Windows users, this is Control Shift M. For my Mac users, you're going to use the Command Shift the Command Shift M. For my Windows users, one more time, sorry, it's Control Shift M. And for my Mac users, it's Command Shift M. So Command Shift M. And so I'm going to say that from the immersive data that will automatically generate, because it's in my global environment, my pipe is going to come after that data set is, or that data frame is referenced. I'm going to go ahead and hit return. I'm going to use the ggplot function or package, ggplot, and that's in packet the ggplot package 2, and or the second one rather. And then I'm going to, in the parentheses, type out AES for aesthetic mapping that is located, or that is an argument within this function here. You always have to do this. Always, always, always. And then I'm going to tell R that I want a plane or a plot with an X and Y axis, where my X axis, I'm going to be plotting time spent. So time underscore spent, followed by comma. And then on my Y axis, I want this to be my cognitive load. So I'm going to start topping out cognitive load. And then I'm going to add the points by go ahead and hitting Shift plus, and then I'm going to type out geom underscore point. Now I have memorized this. You can actually go into the documentation for ggplots, and you can look at all the different ways that you can actually end up plotting the uh, plotting the data the way that you would like to. All right, let me make sure I have everything in here the way that I want it. It looks right. And so I'm going to go ahead and run this. You can either hit the play function, or you can go ahead and come at the end of that code there, and you can hit command return. And then you can actually see that I have my plot here, and you can see this curved trend, right? You can see the curved trend. And I forgot that I was actually trying to also add a linear function or a linear trend on top of this. And how I can go ahead and I can add that linear term is I can go ahead and hit plus. So you can already see on the data that there's that curve. Plus, and then go ahead and type out geom underscore smooth. And so what this is going to do is it's going to plot on top of my own data trend a smooth linear trend, right? Smooth. And then within smooth, go ahead and type out method. And then within method, you want to go ahead and have it equal to a linear model. A smooth linear model is what we want to add. And then you can go ahead and run that again. And then you can see the linear trend plotted onto that curve trend. And so this is one way that you can go ahead and see kind of the difference, or the difference between the data trend and an actual like linear trend. Okay. And one more time, this is already an indication that we should be using a polynomial regression. But there are other things that we can actually do. For instance, we can use the plot function, where we can go ahead and plot our findings here, and you can see different deviations from the linear trend here. So I am going to create a new R code chunk. I'm first going to start off with a header. I'm going to put plots. This should be a second level because I already have my assumptions check levels. I'm going to type out plots. And then I'm going to do Option Command I for a new R code chunk for my Windows users. One more time, Control Alt I, Control Alt I. And so you can go ahead and type out plot. And then you want to, within that plot function, go ahead and type out the model name. In this case, it was model LM. Okay. And I'm going to do that. And so I'm going to navigate to the first plot here. This first plot is called the residual versus the fitted values plot. And so on the x-axis here, rather, I have my fitted values, my predicted values, my y hat. In this case, this is going to be cognitive load, my predicted cognitive load from time spent. And then I have the residuals. How far away are my actual data points from this linear line? And you can see that there is some sort of bend in this relationship between my residuals and my fitted values. One more time, this is an indication that we are deviating from linearity, that our model shouldn't, that our data really aren't representing a linear trend, but some sort of bend, some sort of trend is happening besides the linear one. Okay. What we would actually like to see is that we would like to see all of these points scattered across the values, the fitted values, and that there is no pattern, that our residuals don't make up some sort of trend, and that we want them stationed around zero, right? We want our residuals to be as close as to zero as possible, suggesting that our model is fitting the data so well using a linear model. That is not the case one more time. All right, let's go to our next one. So the QQ plot. As you can see within the QQ plot, we also have some sort of weird pattern happening. I love the QQ plot. It really does a great job at plotting our residuals. And so what these theoretical quantities are is if we took our relationship between our cognitive load and our time spent, we would go ahead and have some sort of quantiles of these theoretical values. Okay, so you can see plotted from 0 to 2. And so we want all of our points to be on this trended line, this dotted line, if you can see it here. We want all of them to follow that perfect linear relationship, the hypothetical linear relationship. That is not the case. Another thing that the QQ plot starts to point out are possible outliers, people who are really deviating from the linear trend. So I believe we have 16 and 29 and then another value. Kind of difficult to see, but you can blow up this this plot here by using this extension right here, show in a new window. It's just a little button that is located within the plots itself. All right. And then you also have, for instance, you have your fitted values against your standardized residuals, excuse me. And one more time, we don't want a this weird little pattern. Rather, we want a flat pattern, just like straight across. One more time, we're just looking for just deviations around linearity. And so now we're going to start getting into outlier plots, which is a part of understanding or assumptions checking. And so one of the plots that we are going to actually see here is that we are going to see a residuals versus a leverage plot. And so let's talk a little bit about this, because one more time, understanding or identifying outliers is a huge part of checking your model and checking your data. And so then within this plot, we technically have two pieces of information. We're going to have our Cook's distance information, and we're going to have leverage information. Okay. On the x-axis, I have that leverage. And then on the y-axis, I have standardized residuals. We also have Cook's distance within the plot itself. What is Cook's distance? Well, Cook's distance is actually a diagnostic tool for determining whether an observation disproportionately influences the result. How this technique actually happens is that it models a linear trend with and without every single case, and then it determines the distance or the difference between each model given that you have taken out that case. This is a fabulous technique. Okay, so it's literally all we're doing is plotting Cook's distances across the cases against each other. And for leverage, this is another tool that we can use to determine whether an observation is is truly extreme in the explanatory variable. Rather, another way to say this is technically the time spent, that value for a specific observation for a specific student, really far away from all others. And one more time, we're trying to get the distance. So the greater the distance a student is, meaning the more extreme a student is in that specific value, the greater the potential that that case has on the model itself. And so we really want to understand and identify those points. So on the x-axis, if someone is very, very far to the right, that is an indication that this case has high leverage, has a high influence, right? Another thing that we want to see is that our residuals, we want them to be as close as to zero, that dotted line right there, as possible, suggesting that my case, my points are really being explained by the linear model, and we can see that that's already not the case. I went ahead and in my HTML file here, I show you the Cook's distance to give you a little bit more of a visual aid to help you out. And you can see that, for instance, case 16, case 19, and case 29, when they are removed individually when modeling this relationship, you can see that they're highly influential, right? That they have a far distance, meaning that that when these people are excluded, they are influencing the linear model. All right. One more time, an indication that those cases are influential. All right. And then a visual inspection of our residual versus our leverage. And we can see that a visual inspection of the residual versus leverage suggests that cases 16, 29, and 19 are, are influential, right? And that they're even almost passing that Cook's distance threshold. So everything up above has given us some sort of indication on that there could be a non-linear trend, that we should be using some sort of cubic transformation or some sort of squaring transformation for those x variables or those explanatory variables. Another thing is that there could also be outliers. In this case, when I'm thinking that there's some sort of linear trend, I would keep those outliers just in case if those outliers are due to some sort of different pattern or some sort of different trend that needs to be modeled. So I would keep them first before removing them. And I would go for and run a polynomial regression. Okay. So let's run a polynomial regression. To run the polynomial regression, we're going to get a new R code chunk. So Option Command I, Option Command I. For my Windows users, Control Alt I. And so we're going to use the LM function because our beta coefficients are modeled linearly, as I previously noted. So LM, just like we did in the linear model, and then cognitive underscore load. And then we're going to use the tilde sign. And then we're going to use the poly function, Poly. And within the poly function, I'm going to put the explanatory variable time underscore spent. And I'm going to take this time spent to the cube. The reason why is because up above in my first plot here, I can see that there might actually just be a small bend. So I was thinking maybe of squaring it, but I want to use the backward method. So that means I'm going to take it beyond just what I believe the trend should be and make it a little more complex. So I'm taking it to the cube one more time. And then after I go ahead and specify that poly term, I'm going to go ahead and hit comma and then data, and then equals, and it's going to be that immersive data that is already within my environment. So I can find it in the global environment, do that drop down menu, selecting it, and then hitting return. I'm going to be assigning this new linear model to a object. So when I go ahead and I do that into an object, it's going to then be referenced later on. So I can gather that summary data. So I'm going to type out model underscore 3 for model 3, taking that time spent to a cubed. You can use the equal sign or the assignment operator there. I'm just going to use the equal and then go ahead and run that. When you run that, you now have that cubed function or that cubed regression model in your environment. I just want to go ahead and take a peek at it using the summary function. So I type out summary. I go ahead and hit return. And then I'm going to type out model underscore and then 3. And we can go ahead and evaluate this by running that option, or rather that function. Let me pull this down a little bit. And so what we can see here, when we look at our output, we have first the linear trend, right? Linear trend. You can see poly time spent, comma 3, and then 1 for the linear trend. I'm just gonna actually pull this over. I'm just gonna use my HTML file. That way it's a little bit neater. So you can see the linear trend, it is significant. Also, that squared term is also, right, the power time spent to the power of 2 is also significant. But if I look at that cube term, it's not significant, suggesting that a cube trend does not thus explain the relationship between time spent and my cognitive load. This is when I would then move on to implementing a square term. So on line 56, I'm going to employ another R code chunk by using the shortcut key Option Command I or Control Alt I. And then I am going to go ahead and type out here LM for linear model, and then my open and close parenthesis. And then I'm going to type out cognitive load underscore load because it is the response variable. And I'm predicting that by a polynomial, so poly. And then within that polynomial argument or function, I'm going to go ahead and type out the explanatory variable time underscore spent and then comma. And I'm taking that time spent to a second degree, meaning I'm squaring time spent. After that, I'm telling R that that data is actually in my immersive data set. Okay. And then I'm going to assign this to a model, or I'm giving this model a name. So I'm just going to type out model underscore 2. And then I'm just going to run this. At the end of that function there, I just go ahead and hit command return. And then I am going then to ask for the summary information by typing out summary. And then from there, I'm going to type in the model name, model underscore 2. And then you can see all of my summary statistics there for the second model. And the second model actually is showing that when we go ahead and square that term time spent, or rather when we use when we take time spent to a second degree, that relationship is significant. And so one more time, this is suggesting that the quadratic model suggests that time spent model using quadratic function or taking it to a second degree significantly predicts cognitive load. And you can see how when it comes down to interpreting this type of finding, that it gets a little cumbersome and you have to use extra words. after you go ahead and you evaluate and determine the best model, you can also, you want to take a look at your model R squared. You want to take a look at your F statistic to understand that the model is truly well fitted. You can evaluate model fit also by using your plots that I showed you earlier. And so let's just do that together. I'm going to add another level, and I'm just going to another level header, and I'm just going to type out plots here. I'm going to then insert another R code chunk using Option Command I or Control Alt I. And then I'm going to type out plot is my function here. And then I'm going to type out the model that I want to evaluate, and that's going to be model 2. And so after I go ahead and type that out, I'm going to hit Command and Return, or you can go ahead and use that play button if you'd like to. And all those same 4 plots that we had seen and that I explained earlier are then generated. So let's take some time to look at them real quick. So my residuals versus my fitted, one more time. I have my fitted values, my y hat values, my predicted values from cognitive load being explained by time spent, right? And then you have our residuals. And what we want to see in this particular type of plot is that we don't want to see any type of pattern here, right? We want every dot to be around 0, suggesting that our residuals are very small, very close to that curved trend line. And then here again in my QQ residuals, the same thing is happening here. I love the fact that we are very close to that line there, suggesting that we're fitting the trend just a little bit better. We still have some outliers, and this time, look at those outliers are actually different individuals. And so then that would suggest that we still have outliers and that we can take care of them some way, somehow. All right, and let's go down. We can take a look at our residuals versus our leverage one more time. When there's influential values, they're going to be located more towards the right side of our plot here. And so the higher they are, the suggests that, or the more towards the right suggests that they have more influence on our relationship. And also, we don't want anything going beyond the Cook's distance line, suggesting that they are really highly influential. And in this case, we don't have anything like that that is happening. So even though we have some sort of outliers pointed out here, they may not be influential. And I think these plots do a great job by identifying those actual cases and observations. Okay, but one more time, they are not going beyond the Cook's distance line. It's pretty contained within my graph here. All right. And so a quick interpretation, how would we interpret this model as a whole? So we would go ahead and try to explain that relationship between the time spent in virtual reality excuse me, and cognitive load. So time spent in a virtual reality course squared is a significant predictor in the quadratic model. And you would go ahead and you would list your F statistic, and you would go ahead and suggest that approximately 99% of the variation in cognitive load is explained by taking into account quadratic function of time spent in a virtual reality course, bringing it back into context and where we are applying this particular regression equation. Okay. And so I do want to just really note here and suggest here that you wouldn't want to try to explain those beta coefficients because they are cubed and because it wouldn't make sense if, sorry, not cube, but rather squared, if rather in the cube function, in the cube regression sense, it would be very cumbersome to go ahead and to try to explain each one of those beta terms. So you typically will not see those beta terms explained, but rather the whole entire model in general explained. All right, So that concludes our polynomial regression section here. And I hope this was useful. Please reach out to me if you have any questions. Don't hesitate. All right. Take care, y'all.